Welcome everybody to week 6, day 1. Your homework assignment is going to be due on Thursday, start of class. And the probably the hardest part of it is the I/O side of things. I think the code itself isn't too bad. Like if you've got a vector and another vector and you need to do the intersection, like let's say you got a vector of strings and a vector of strings, finding out which strings are on both of them is pretty easy, I think. There's one little tricky bit, which I'll show you. But we need to talk about doing I/O. So let's do this. All true. Vector of strings named A and B. So we're gonna fill up two sets of strings, basically. Maybe a better data structure would be set, but whatever. Most people know vectors, so I'll just use that for now. Sets have a better big O time. So I'm just gonna do something like this: string s is equal to read, or we'll do it the old-fashioned way, cn into s if s is equal to quit, then break. You're not going to do this input for your homework assignment, by the way. I'm just getting vectors A and B ready. If not, then we will a dot push back s, and then we'll do this again. So this is going to fill vectors with strings, and then we want to find out which strings are in common for both of them, right? And so a lot of students will do something like this for every string. For every string s and a, for every string t and b, if s equals t, see out. Okay. And this general pattern, by the way, is fine. Whenever you do intersection, whenever you say, give me people that are in both sets, typically at a very high philosophical level, it's typically implemented some sort of like nested for loop. Like this structure is the structure for maybe more philosophy, but it's what set intersection looks like. Whereas set union looks like this: for string s and a, c out s. And of course, neither of these are correct, right? But just at a very high philosophical level, intersection is going to look like a nested for loop, whereas union is going to look kind of like a parallel for loop. We're going to do everybody in A, we're going to do everybody in B, all right? For union. Do you guys understand intersection and union? Like, you guys got that down? You guys awake? Need coffee? Can you review it real quick? Sure. Oh, my wife's calling. Yeah. Alright, so let's review set intersection. Okay. So let's maybe draw this one out graphically. So if I have a set, which I'll call A, and a set that I'll call B, intersection is this part right here. Intersection is the elements that are in common of both of them. So if A has got like Obama, Trump, and Biden in it, B has Biden, book, shelf, and banana. Set of things start with B. And then A is presidents or something. I don't know. So if you intersect Obama, Trump, and Biden, so A is Obama, Trump, and Biden, and B is Biden, banana. I'm not writing the whole thing out. And bookshelf. If you do A intersect B, then that returns another set. Set intersection is an operation that takes two sets as input and returns one set as output. And if there's nothing in between the two, it would return null set. Null set means there's nothing in the set. Okay. But in this case, we got Biden in both, so it's going to return Biden. Okay. I should have written Biden out for all these, but I don't want to waste time. So, union. Okay. So if I union Obama, Trump, and Biden, and bookshelf, Biden, banana, then that returns all 5 of them. Okay, so A union B is equal to Obama, Trump, Biden, banana, and bookshelf. Okay. You don't output banana. You don't output Biden twice because you have to remove duplicates. Okay. So, do you guys understand that? Intersect and union. We typically use like Venn diagrams to do this kind of stuff. And if you understand this, then and you do the homework assignment, which is due on Thursday. It's a 20-pointer, so partner with somebody if you have to. Although that does carry the risk of one person just doing all the work, which is a downside, but it is a tricky homework assignment. So if you can do the homework assignment, then the syntax I'm using for it is not exactly, but more or less what's called MySQL, which is, or SQL, I should just more broadly put it. SQL is the database query language, structured query language, but it's used for querying databases. So if you've got a database set up and you want to find out, give me all customers that are between the ages of 40 and 50, male, live in these zip codes, that's a SQL query. And what you're doing is you're doing a set intersection between the set of all male customers between 40 and 50, or set of all males, set of all customers that are between 40 and 50, and set of all customers that live in these zip codes. You do an intersect and intersect and intersect, and then the query returns to you the set of all customers that match those things. And this is a very, very common thing to do. It's a super common thing for businesses to do. For customer management's a big, crucial part of success. There's customer relations management, CRM software or whatever, like constant contact and things like that. And is vector the ideal data structure for this assignment? No, but it's the easiest one to write. So, set is real. I mean, these are sets, right? We're doing set theory. We're programming set theory. But then your strings are going to output in a different order than mine, which is not wrong, by the way. If you're failing the autograder tests because they're just coming out of the wrong order, it's fine. Like, don't worry about it. You don't, just message me and I'll grade it manually. Okay. I don't punish people for trivial things like that. So as far as efficiency goes, set's better, but everyone knows vectors, so I'll just show it with vectors. Yeah, and so like I mentioned before, if you know SQL, you can get paid. It's the kind of thing that you can just kind of get a job anywhere in the world doing SQL stuff. It's not even necessarily that difficult most of the time, but there's a lot of work in it because every business needs to have a database. My business has a database, and my business has attendance records. I do a lot of educational research, and so it contains attendance records and test data and I don't know, all sorts of stuff. And then I mine the data. I do analysis, and that's bread and butter. Yeah. All right. So let's hop back over here, server, and anyone know what's wrong with these two things? What's wrong with set intersection? What's wrong with set union? I told you it looks something like this. It's not exactly right. What's wrong with it? Anyone see the bug? Union will print duplicates. Sure. So rather than outputting it directly, we would have to add them to a set, right? And then or check for duplicates every time you add some. Like if you're going to be making a union vector, then check to see if it's in the vector before adding it to the end, which is going to be terrible from a big O perspective, right? Is instead of just push backing a string, you're now checking to see if it's in the vector every time. So you've just turned an order in operation to order in squared. It could be sped up, I guess, by just adding all of them, sorting them, and uniquing them, which would put it into order in log n time. Should be the same running time as set, I guess. Oh, you can do it that way. Anyone see the bug in intersect? No? Maybe there was no bug. Maybe that was a trick question. Well, Alpisco's been running this for 1 hour, and this one 47 minutes, and this one 20 minutes. Yeah, I'm gonna kill that. Sorry. All right, so A, B, C for our first set, quit. And then B, C, D, F, A, G for second set. Anyone see what the problem is? Can an output set have duplicates in it? Actually, I'm not separating these out. Looks fine. Won't work if there's a duplicate in the strings already, in the sets. But if you assume that these things don't have duplicates in them, looks fine. B, D, F, A, B, C, D, E, F, G. So this is B, D, and A. That's fine. Okay. So should intersect be in sorted order. So yeah, like I said, it doesn't really matter to me too much the order that you print things out because it's a set. Either something's in the set or it's not in the set. Okay. So yeah, this code doesn't work if there's duplicates in the inputs, but there shouldn't be. Those should be sets already. Okay. So as far as the design of the class, you should make a class for holding a set. Don't call it set, like lowercase set especially, because you're going to conflict with the standard library. That's why whenever I make my own classes, I use a capital letter for them. Then there's never going to be a conflict with the standard library. So every set, every table, should have a name, and it should have a backing store of some sort. You can use a vector, you can use a set, doesn't really matter to me. And like I said, if you get the right answers but in a different order, like A, B, and D, then it's fine. So like if we were to replace this with a set, what's used for the superset class? Well, you've got to have a list of all the different tables, right? So if somebody says insert all values from Lithia into California, you have to be able to, you need to have a table of tables so that you can be like, all right, there's Lithia, there's California, copy up, take all the elements of Lithia and insert them into California. Do a union, essentially. Okay, so let's do this with a set of strings instead. And pushback does not exist in sets because there's no back to a binary tree. Instead, we're going to use insert. And then all the rest of this should work the same. Good. Sorry, Alapisco. Alright, so A, B, C, Z, quit. F, E, A, P, quit. So A is the only thing found in both. That code still works. There is actually a standard library set intersection. So that's the thing. There actually is a set intersection standard library. It's found in algorithm. It requires both of the inputs to it. It's going to take two different data structures like this, like two vectors here, and it requires them to be sorted. So you either have to call sort on the vector, or you have to use a set, which is always sorted. And then you call set intersection. It takes from vector 1 beginning to end, vector 2 beginning to end, and then it's going to insert them at the back of this new vector here. So that's, yeah, that basically says put it at the back of V intersection. It doesn't matter if it goes to the back or the, well, I guess it does. Yeah. So insert at the back of the intersection, and then it will fill it with all of the elements in common between these two, which is going to be 5 and 7. And then we say for every element in V intersection, output it, and we get 5 and 7. So that's the thing that exists. I don't know if that's any easier than than this. So, yeah. If you want to be super C++, you can use the standard library, or you can write it yourself. Okay. Yeah, so for set union, you could use set string output, and then for every element in A, rather than just dumping it to the screen, we can say output dot insert S. So did you guys see how I changed that? So rather than just couting it directly, what I'm doing is I'm putting everybody into a set, or you can use a vector for it. It's fine, and just remove duplicates. So the set standard library class removes duplicates for you. It's a set, so you don't even have to worry about it. So, yeah. And then we just say for every string in output, put the string. A, B, C, Z, B, C, Q, 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 T. You'll see that Q only appears once because we're inserting into a set. It removes duplicates for us automatically. B and C are the only ones that appear in both. And A, B, C, Q, T, Z is the union. So, there you go. So, if you guys don't know the set data structure, probably worth learning it. It's not actually that hard to learn. Like, you hashtag include set, make a set of strings, and you call insert instead of pushback. I don't know if you even have to erase anything from it for this assignment. I don't know. Probably just this is good enough. Let's see what set's got if you're into that kind of stuff. How many elements are in it? Count tells you, is that in what? C++ 14, yeah. Template class. Oh, interesting. Okay. Yeah, count tells you basically if something is in the set or not. It returns the count, which is how many times does Q appear in the set. It's either going to be 0 or 1, right? So you might as well consider this like a Boolean instead of size type, because, yeah. Right, because it's a set. There's no duplicates. How many bananas are in the set? It's either going to be 1 or 0. And so you might as well think of that as a Boolean, rather than returning an int, which is kind of what it is, an unsigned 64-bit int. Find returns a pointer, or returns an iterator, technically, to the thing you're searching for. You then need to dereference it if you want to output the value. So if you're going to search for the number 2, then if it's not found, it returns a pointer to end. And I use the term pointer and iterator interchangeably because conceptually an iterator is just a C++ version of a pointer. They're not pointers. Like, in the language itself, they're completely different. An iterator is a class. A pointer is a primitive type of the language that holds just a memory value. An iterator, though, is a generalization of the concept of a pointer. So it has functions on it and useful stuff like that. So yeah, but I'll just say pointer. So even though it's not accurate. So we're going to search for 2, and that returns an iterator. You know it's an iterator because he used auto. The type name of iterators is usually pretty long and kind of garbage looking. So that's how you know that's an iterator usually. That's in my opinion why the auto keyword was invented, so you don't have to type out those long things. Does primitive mean obsolete? No. Primitive means that it is a built-in part of the language. So almost nothing we do in C++ is part of well, I shouldn't say that. The int, float, double, bool, char, pointers, they're all a core part of the C++ language. Pretty much everything else we do is part of the standard library. It's not part of the C++ language. Like if you didn't include set, then like none of this stuff would work. You know what I mean? Okay, so yeah, find returns a pointer, an iterator to this fellow right here. And if it was not found, then it would return a pointer to end. End is a pointer to an element off the end of the data structure. So this is the beginning. One, if you return example.begin, example.begin is a pointer to here. Example.end is a pointer to one past the end of the array. And the reason why we do that is because the way we do for loops, we say for int I equals 0, I is less than size I plus plus. The pointer equivalent of it is for auto I equals example.begin, as long as I is not equal to example.end, I plus plus. And so, how do we check the VIN if it's uppercase? Use isUpper. There's an isUpper function. So for every character in the string, if not isUpper, or you can use isLower, it's probably better. Is better. If is lower, then die, or whatever. Okay, so anyway, so end, example.end is a pointer to here, like right here. And if any function like find doesn't find it, then it returns a pointer to the end. And that tells you it's not found. Otherwise, it gives you a pointer at the element that was found. And then you can dereference it. And that's the part that people always forget. Is you can't just see out an iterator, you have to dereference it to get the value, in this case 2. Yeah, and then contains is a bool, true or false, which is essentially exactly the same thing as count. But they're adding contains, yeah. And yeah, that's about it. That's your set data structure. Okay. So basically you can insert, search, and delete. Insert is by calling insert. Search is called using find or count or contains. They kind of more or less do the same thing in different ways. There's kind of no point to using find because it's like, sure, it returns you. I guess there is a point. I should take that back. But if you're just doing something like this, where you're just like, I'm going to print out 2. Well, you know what you're printing out. It's 2 because you search for 2, right? Like, if you're just doing something like this, I would just use contains or count, which are all 3 of these are more or less the same. Find, though, sometimes you want to have that iterator returned because, like, if you want to erase something, here, if you want to erase something from it, you need to pass in an iterator. So if you want to delete something out of a set, which I don't think you need for the Sunworks assignment, but I'll just go over it anyway. So you got the set here, which is going to be 1, 2, 3, 4. All these duplicates are going to be vanished. They make a lambda. That's funny. And then they're saving this as kind of like a function object. Okay, so they make a lambda to print out the set, which is going to say for every element in the set, print it with a bracket at the beginning and end. So it's cool. So they call print, and it's going to be 1, 2, 3, 4 because the duplicates are deleted already. And then this one they're just erasing by just iterating through the tree, which is kind of weird. Normally you'd use erase with find. And so normally you pass erase an iterator, and it erases that element out of the tree. Okay. I guess you could do it this way. That's fine. So you go from the beginning to the end, and if the value held is odd, then erase it. So I guess fine. And then when you call erase, it returns an iterator to the next element, so it doesn't. So you don't have a bad pointer, essentially. You don't have an iterator pointing at something that doesn't exist anymore. So you need to do that. Yep. But normally erase combines with find, right? So you do a search. Is Sally in the set? No? Okay, well, do nothing. Yes? Okay, pass that pointer we got back, pass it to erase. And then it will delete Sally out of the tree. And that's it. I mean, really, set is a really simple data structure. It's got big O log n running time for pretty much everything. It's pretty fast. Insert is order log n. Erase is order log n. Search is order log n. So, and the thing will tell you complexity. There we go. Logarithmic. Okay. And they have, let's see, constant running time for the hint. Interesting. Yeah, there is a way of speeding it up, but basically what you're looking for is logarithmic. That means order log n. So inserting is order log n. Searching is going to be order log n. Complexity logarithmic, and erasing is going to be order log n also. Amortized constant if what is it? Version 1 const iterator pause. Oh, right. Yeah, if you've already found it, if you've already found a pointer to the spot you're going to erase, then that's actually constant running time because it just moves the pointers around. Yeah. But if you pass in something you're searching for, then oh, that's right. Yeah, you don't even need to do it with find. You can actually just pass in a key, and it will do the find and delete it if it exists. And that's also login. So cool. Sets or BSTs, yeah. Probably. There's no guarantee it's implemented as a BST. It could be implemented however the standard library author wants to do it. But if you want to think of them as a BST, you're not wrong. Because all of the running times for a set are the running times for a BST. And so, but you could implement it as like an array. That's fairly common. Where you just, then you don't need to have pointers. Right? If you put everything into an array, your parent is your index divided by 2, and your kids are your index times 2 plus 1 and plus 2. And so you don't have to store pointers everywhere as long as you can guarantee that the tree is fairly compact, which you can when you're writing it. Then you don't have the overhead of all those different pointers hanging out. And you can also find your parent easily. So you don't have to have a parent pointer either. Are BSTs widely used in the industry? Yeah, I mean they're like one of the core. They're like one of the core data structures. I mean, hash tables are faster for insert, search, and delete, but they aren't sorted. Right? That's why if you wanted to do a hash table, it would be, unordered. You know what I'm saying? That's a hash table now. So it depends what you need. Like if you need everything to be sorted all the time, then you use a set. Like it just really just kind of comes down to your individual problem, and the needs of your problem. Okay, so let's talk about input. All right. So no, it's a good question because like I always talk up hash tables and how important they are, and they are very important. They're my favorite, they're my favorite by far. But, if you need things constantly to be sorted, that's, and to eliminate duplicates, you'd use a set. If you want to allow duplicates, there is multi-set, which, it's just here, multi-set. Yeah. So it's included in set. So if you want to allow duplicates, you make a multi-set. Okay. If you do a set, do you have to make a less than operator for set insert? If you're just inserting strings, you don't have to. If you're making a set of your own data type, then you have to make a operator less than. So the set class itself requires whatever is within the angle brackets here to have an operator less than on them, or equivalent. Okay. And the string class implements operator less than. Okay, so let's talk about I/O. Good questions. Let's talk about I/O. So this is something we talk about in 40, and you never get tired of talking about, I guess, because handling input is one of the more annoying parts of programming, right? Because you're just like, hey user, give me your name, and they can type literally anything they want. You know what I mean? Like, you think they're going to type like Bill, but they type like Bill Kearney, and now you got 2 words instead of 1 word. And like, you know what I mean? Or like, think about how complicated it would be to write a program that handles phone numbers. They can take, the user types in something, and then you say whether or not that is a phone number or not. Can you think about how garbage that is? How hard a problem that is? Seems easy, but it's not. This is, in fact, my brother-in-law, he uses this as his job interview question. So when he's hiring a new programmer, he hands them a database of a huge number of strings. The strings contain supposedly phone numbers, and you're supposed to sort them into valid and invalid. Then you got half an hour. Go. How do you do it? How do you determine if something is a phone number or not? Right? I mean, think about how many different ways people can type phone numbers, right? Area code 559, 555, 1212, 559, 555, 1212, 559, 555, 1212. You know what I'm getting at? Hyphens, no hyphens, parentheses, no parentheses. Some numbers are not allowed, like 156, 555, 1212. That's not a legal phone number. Can't have an area code that starts with a 1. Like, in fact, the first 3 the first 3 digits here in your actual phone number actually correspond to a region within your zip code. That can't start with a 1 either. That's not allowed. Can't start with a 0 either. That's not allowed either. So there's all sorts of rules that a lot of people aren't even aware of for phone numbers. First ask questions to specify what is a valid number. Yeah, sure. Yeah. Okay. Give me the rules. Then you have half an hour. And he doesn't expect that you finish it. He wants to see how you spend your time, because he wants to see you get as many numbers sorted into valid or invalid as possible, as accurately as possible, in half an hour. Okay? So, do you like, some people, I don't know, might use brackets or something? I don't know. Some people use spaces, some people use hyphens. Like, it's, he wants to see your approach towards it. And that is annoying. Again, people can type in anything, They don't even have to type in a number. They could be like, whatever, this is my phone number, Okay, so dangers of mixing the approaches. All right, we'll talk about that too. So, I/O, input-output, okay? And so in C++, there's 3 different ways that you can read from the keyboard. And really, if you can read from the keyboard, reading from a file, reading from the network, they're all more or less the same. Okay, network's a little bit different, but because we do input redirection in Unix, even if you are reading from the keyboard, oftentimes you're not reading from the keyboard, you're reading from a file instead. You just don't know about it. So there's 3 different ways you can read. You can read one variable. If you cn into an int, you're reading one int at a time. If you're cnning into a string, you're reading one string at a time. So this is what most people use in CSI 40. They do that. That is not sufficient for this assignment, because this assignment you're going to be getting things like this, like insert values into California, or was it insert into California values Pinto, Chief, Jello, Apple. Okay, so if you were to read a string, it would just grab that whole thing for you. Right? So not sufficient. Okay. So we need to dig into it a little bit. So there's three options. There's double right arrow. There's get line, which returns until the next new line by default. Last time we talked about get line being able to read until a certain character is passed in. Very useful to read until a comma is passed in. Right. Get reads one character at a time. So if you call get, it returns you I. Okay, and then you call get again, and it returns N. Okay, and if you really want to go hardcore into it, you can build your own parser that reads one character at a time, and once you hit a space, you're like, okay, that's a word, and you like go through a branch, and then you read a character at a time. And if you ever hit a new line, because it'll give you a new line if you want, you're done with the line, and you can. I've seen students do that, and they parse this whole thing out. So they read this, and then when they get to a comma, they throw the comma away, and they throw that into the data structure, and they clear it, and do it again. So you can, if you use get, you can read one letter at a time, and I'm going to tell you, your code is going to be an order of magnitude bigger than it should be. That's how I wrote some of my code in 41 when I took it back in the day, and it gets complicated. And there's also a command called unget that actually puts it back into the input buffer. So you can actually read a character out, look at it, and be like, oh, shoot, that's a number, isn't it? I thought we were reading a letter. So we must be now in the next phase of input, and I've already sucked one of the numbers out. So I'm just going to very quietly push it back into the input buffer. I'm just going to go, oops, my bad, and just, do that. Let's wrap it back up and put it back under the Christmas tree. So unget is a command a lot of people don't know about. You can actually push things back into CN. So we're used to CN being a one-way street, right? Data comes out of CN. You can actually shove things back up into there if you want. And it doesn't even have to be the same character that it was originally. You can unget anything into it if you want. Okay. In general, though, these three things do not play nicely with each other. If you mix and match these three things, your code's probably going to break. Okay? And to understand why it breaks, you have to understand what's going on with CN. Okay? So, if you do a CN into X, where X is an integer, what it does is it throws away any white space before the number. Okay? So when the user types in something, by the way, space, 5, space, 6, space, 7, return, all of that, nothing appears in CN. CN doesn't see anything until the user hits return, hits the enter key, okay? Because by default, CN is in what's called baked mode or cooked mode, and it will not see any input until the user hits enter. Okay. If you want to turn off cooked mode and go into raw mode where you get individual keystrokes, I've written a library to do that because it annoys me that C++ doesn't have the ability to turn on raw mode. It's just always in cooked mode by default. 40kid was stuck, yeah. So you have an input buffer, and you can think of this as like an array. It's not exactly, but you can think of it as an array with each character in the input buffer. And when you do a CN, like CN into X, this integer here, cin throws away white space. It throws away all of the white space prior to the 5. So it reads one character at a time, goes, hey, is this a number? Nope. Throw it away. Hey, is this a number? Nope. Throw it away. Hey, is this a number? Nope. Throw it away. Oh, a number. Cool. So I'm going to start reading numbers now. And let's make it a little more interesting. Let's make it a multi-digit number. So you read a 5, it's like, okay, cool. We have found a 5. The error bit's not going to be set. If we found like an X or a squirrel, right? S, it would set the fail bit. The operation would fail, and all future cin double right arrows would die as well until you clear the fail bit. But in this case, we're good. We found a digit. So now it is in the I'm reading digits mode, and it will keep reading digits until it doesn't, until it finds a space or a letter. So it reads the 5, cool. My current value is 5. And then it reads the next one. Oh, cool, another number. So the 5 turns into a 50. It gets shifted left one digit. So the 5 becomes a 50, and then it adds in the 5. So it's now 55. Cool. Now it reads in the next digit. 9. Okay, the 55 turns into 550. Shifts left one digit. 55, 550, added 9, 559. Cool. Keep going. Maybe we'll get another digit. Nope, we got a space. All right, done. Wrap it up, put a bow on it, and stuff it into X. So 559 is the value that is going to be placed into X. And then when we're done with this, all that white space is gone, 559 is gone, and there is, in the input buffer, space, 6, space, 1 or 2 spaces, I don't know, 7, and new line. Okay? So cin double right arrow consumes white space prior to the number. Okay? And if they type in something that isn't a number, then it fails and the fail bit is set and you have to handle it. Okay? So every time you do a cin double right arrow, you need to follow it up with a if not cin to see if an error occurred. And if it did, you need to handle the error. Okay? So cin.clear clears the fail bit so you can read again. And cin.ignore will throw away all of the, it ignores a certain number of characters. Or you can cin into a string, and that will pull out 559 only. So it'll preserve the remaining numbers. Or you can cin ignore and just throw away all the input buffer if you want. Yeah, so that's what's happening with double right arrow. Do you guys understand this? It throws away leading white space, not trailing white space. We're going to get through this and we'll take a break. We're going to get through this. Okay. GetLine works differently. GetLine, let's say the user types in so you can type in space, 559, space 6, space 7. All of that will be copied into sentence except for the new line. So leading white space is not discarded. All of it gets sucked up. And the 559 and the spaces, all of that gets stuffed into sentence. However, the trailing new line is discarded. And that's different from cin. If you cin 559, space 6, space 7, 559 gets stuck into X. If you do it again, 6 gets put into X. If you do it again, 7 gets put into X. And there is still a new line in the input buffer. With getLine, it eats the new line at the end of the line. And this is the source of conflict between double right arrow and getLine, is because cin leaves the new line after a read, getLine discards it. And so if you do a cin followed by a getLine, and all there is in there is a new line in the input buffer, getLine's like empty string, there you go. And that confuses the hell out of students. Okay. So so it grabs all the white space before, which cin doesn't, but more importantly, it destroys this one. And then there's a third kind of getLine where you pass in the character you want to read until, and it will read up to that character and discard that character, and then return everything before that into the string. Okay. So the function of the third parameter, we can specify the end of the read. Yeah, but here's the kicker. It doesn't end, right? Like if I say getLine until a comma, and there's no comma, it will just keep reading. It doesn't also stop on a new line. It stops only on a comma, and so you can't just use it. You can't just use it on a raw thing like this, because eventually you're going to get to the end and there's no comma there. So, so we need to use the string stream thing that we talked about. So, do we have nothing on? Okay, there we go. That's weird. Well, I mean, that's the obvious next thing. But the third way of reading things is using get. So, it's PowerPoint and action are there. So, get and unget are completely fine-grained control, right? If you get a letter, it will give you white space. It'll give you a new line. It doesn't do any like fancy schmancy processing. Cin can be turned. There's options for like no skip WS for like how you process white space and things like that for double right arrow. But in general, get and unget give you the best control over processing your input. It's also a pain in the ass to work with, and I never use it these days. I've discovered better methods than get and unget. But you can. It's there for you if you want. So this just returns a character that puts the character back into the input buffer. And if you want to just see what the next letter is, you call peek. And so that's pretty common. You can do a cin.peek and find out if the first letter of the next thing is a letter or a number. So if it's a number, you read it into an integer. If it's a letter, you read it into a string. And then you don't have any problems with cin becoming invalid, right? If you read ints only into ints and strings only into strings, then you're not going to get the problem with a squirrel appearing in your number. Okay. So peek is very useful. Hey, tell me what the next character is, and then you can be like, if it's a digit, do this. If it's an alpha, do this. If it's a space, do this. What is the purpose of cin grabbing the new line? Because it reads until a new line, and so if you're going to be doing multiple get lines, it has to destroy the new line. Because get line. If it didn't destroy the new line, the next time you called get line, it would just return an empty string, and then you call it again, and it returns the empty string. So get line has to consume the new line after it. But double left arrow doesn't, because it doesn't mess with anything after the variable. And so combining these two things just causes conflict and contention. You generally want to stick to one or the other, unless you know what you're doing. So that's one character at a time. Now, the way I typically work with getLine is like, if you read one line of input at a time, which is fine, just stick to getLine. You can then convert that string that you just grabbed into a string. We talked about this last time in class. So if you getLine this, and you have a string now that contains foobar baz 1066, the last time that England was successfully invaded, although arguably the Glorious Revolution would Why are these spammers so insistent? It's crazy. Glorious Revolution, technically, I think, was a successful invasion as well. William of Orange, William and Mary. So, anyway, if you get line and you get this, then you need to split this big string up into smaller strings. And so it's very common to use get line, convert the string you got into a string stream, and then read from it. So it looks like this down here. So you get line into sentence, and that gives you this whole thing here. And then you convert the sentence into a string stream like this. So you say string stream STS, or you can say I string stream because you're going to be reading from it. Doesn't really matter. We talked a little bit about that last time, but there's an input string stream and output string stream, and just a string stream that does both. Technically for this one it should be an I string stream, but string stream does both, so it's fine. So what we're doing here is we're reading in a string, we're converting the string into a string stream, and then you can read from the string stream like it. You can read from the string like it's a stream. It's a tongue twister. I got it backwards last time too. You can read from the string like it's a stream. Yeah. So now that we have this thing turned into a string stream, we can read from this string here like it is a stream. So the first time we do double right arrow, it reads foo. The next time we read bar. The next time we read baz. The next time we read 1066. Okay. So we get line to grab an entire line of input, which gives us a string containing foo bar baz 1066. We convert it into a string stream, and then we have a while loop while the thing is valid, read from it, and technically we need a break in here. This is actually going to give us a duplicate. Every time you do a double right arrow, you need to check to see if it's valid, right? So if not, STS break. We need that in there. And then this will put each of these strings into this vector here. So what we're doing is we're essentially splitting the string. So given a line of input that contains multiple strings in it, this vector here is going to contain each of the different words. Does string stream ignore commas? String stream just converts the string into a stream. It is agnostic to commas. It just makes this string able to be double right arrowed from. Okay. So you can double right arrow out of the string and pull the first word, the second word, the third word, so on and so forth. So if you wanted to split it by comma, it's going to look like this. That's going to read one entire line until I hit return. And then I'm going to I string stream input. So that converts input into a string stream. And then we can do things like STS into a variable and stuff like that. But we're not. We're just going to make a vector called a vector of strings called split. Let's call it back, whatever. So, so let's say they input 4, 5, 6, 7. Okay. Make it a vector of ints then. So we want to fill this vector of ints. Vec should hold 4, 5, 6, 7 after we're done, right? So it should be a vector of size 4 that holds 4, 5, 6, and 7. And this is very similar to what you have to do for your homework assignment, which is why I'm showing you. So the user types in 4, 5, 6, 7, hits return. Once they hit return, input holds a string holding that string there. We convert it into a string stream so that we can split it, so we can read from it. And then we're going to stuff 4 and 5 and 6 and 7 into the vector using this while string stream. And string stream becomes invalid once you get to the end of it, which is really nice. like is string stream a version of cn? Yeah, you can use a string like it's a stream. That's why it's a string stream. So cn is a stream. It's a IO stream. Okay. So you can double right arrow out of it. You can treat it like cn. Yeah. Except rather than reading from the keyboard, you're reading from a string. So we do this string s, get line from the string stream into s until a comma is read, and then we will make an integer x that's equal to string to integer s. So this is going to return the string 4. We convert the string 4 into the integer 4, and then we vector dot push back. But every time we do a read, we need to say if not sts break. Because if you get to the end of it, it becomes invalid, and so you need to check for that. Okay. And so then at the end of the day, we will say for every integer and back. See how that ends. Well, let's see how this goes. Run. So if we type in 4, 5, 6, 7, we get 4, 5, 6, and 7. So this is a very powerful technique. It isolates input, because normally if you did cn, like if I did a cn into a variable or something, if there's nothing at the end here, it starts reading from the next line, and it's going to cause all sorts of problems, because you want to isolate each line of input is one line on its own. You don't want your cn grabbing things off the start of the next command. You know, be a pain. So this code here will split this string 4, 5, 6, 7 by commas. Each comma is separating the values, so it gets until the next comma, and so that string there would be like s would be like the string 4, and converts the string 4 into integer 4. Okay. Then adds it to the vector. Okay, and so we use this before in 41, yeah, but it's really important to go over, because you need to get IO down pat. Yeah. And then mixing them is a problem as well. If you mix double right arrow with get line, the double right arrow will leave a new line in the input buffer, so that when you do a get line, it says empty string. It destroys the new line, but it just returns an empty string. You're just like, what the hell's going on here? You know, big problem in Pokemon, especially. Get and unget will just give you a white space for a new line, whatever. They don't do any fancy processing. It's basically raw. You know, it's just, here's the characters that the user typed in. Cn discards leading white space. Get line discards trailing new lines. And so the interaction of these things can be a big deal. So the right way to do it, if you're going to be combining, if you want to combine get line and cn and stuff like that, then this is the way to do it. Okay. So make a string, and then that have all of your primary input be get line, get line, get line, get line, get line. And every time you get a line, convert that line into a string stream, and then parse it using double right arrow or whatever. That is the way to succeed. Okay, so let's go ahead and take a 10-minute break, and that should be everything you need to know for the homework assignment. So it's not too bad, I don't think, but the biggest thing is just the amount of IO you have to do. There's just a lot of, like, I've got like 2 or 3 pages of if statements, like if the user types this, then do this, and there's just a lot to it. It's not hard. It's just voluminous. Okay. Can you show the file again? What file? This one? Which file are you talking about? That one? Sure. Yeah, I'll leave it up during break so you can admire it. Yeah, so don't wait to the last minute because there's a reason why it's a 20-point assignment. Okay. So, yeah, there's just a lot of input, and then the actual coding itself, the set intersection, the set union. It's not really that hard. It's a little doubly nested for loop, a little parallel for loop for the union, doubly nested for loop for the intersect. That's it. Okay. So, wasn't it Mr. Mime that's giving people a hard time? Yeah, because all the Pokemon in Gen 1 are a single word, except for Mr. Mime. Mr. Mime is 2 words. And so you either special case it, where you say if the name of the Pokemon is Mr., then you do 1 extra CN, right? And special case it. Or what you do is, because the input files are all comma separated like this, then you get line the whole line for the Pokemon information, and then you split it based on commas, and then just take that whole string, Mr. Mime, and that's your name. So that's the better way of doing it. This is the better way of doing it. So, data. Let's see. Yeah. Oh no, it's tab delimited. Sorry, it's not comma delimited. So then, I added some extra Pokemon like Fistindantilus, the great destroying monster from the depths, which is multiple words for the name. George Clinton. Okay. So, yeah, that was also designed to teach you parsing because it's important. It comes up a lot. Okay. So, gonna take a 10-minute break. We'll come back at 11:25, let's say. 13-minute break. All right. Peace out, you guys. And let's continue. All right. So that's all I'm going to say about the homework assignment. If you have any questions, ask it today, not tomorrow. I think tomorrow I might just go to sleep early. Leave everyone out to dry at 3 o'clock in the morning. Okay, so let's go ahead and talk about more stuff. And so our next big topic, and then look for a competency exam as well on Canvas. Okay, so our next big topic is digital logic and truth tables, things like that. We've kind of gone over this a little bit before, but this is going to show you. It's gonna prepare you actually for CSI 45. So, CSI 45 is a class in which we do assembly programming and also talk about sort of the lowest level of a computer that you need to worry about. Right? Computer science people are software people, right? That's our primary focus. But you got to know a little bit of like what goes on above you and what goes on below you. You know what I'm saying? It's kind of like chemistry people need to know physics because physics is kind of below chemistry, and they kind of need to know a little bit about biology because biology is above chemistry. You know what I'm saying? So like, even though chemistry people focus on the chemistry side of things, you have to kind of know where you're coming from and where you're going, right? And like OChem, right? Organic chemistry is a big deal for bio, right? And if you do organic chemistry and you and they ask you to synthesize on a midterm or something, synthesize this chemical, and you do it and you get the right chemical, but along the way you produced a toxic byproduct, you'll get marked down for it, right? Because that's the level above it. Because the reason why you're probably going to be making, I don't know, caffeine or something is, you know, because it's going to go into like, I don't know, some caffeine pill or something, right? And if you murder the people that take your caffeine pill, it's not going to be very popular. So physics is below chemistry, yeah. Mm-hmm. Yeah, because ultimately, like, you've got H2O, right? You got, you know, the three little balls, you know, they're bouncing around. But what's happening when you go down a level is you have electromagnetism, right? And you have these fields. And so you can simulate the physics of the individual atoms if you want. Do what's called Monte Carlo simulations, where you randomly roll dice to figure out, okay, this guy vibrates this way and this guy rotates this way. And then due to electromagnetic attraction and repelling, you know, you can simulate the behavior of water very, very slowly, right? Like you can actually simulate individual water molecules, you know, if you want to. You're going to simulate too few to do anything useful, but like you could simulate it. Oh, I'm not screen sharing. It's fine. I'm just staring at the title screen here. Anyway, so yeah, so you can simulate individual water molecules, and you will do that sometimes to kind of study how they behave, and then you sort of zoom out, right? So once you have an understanding of how it works at a little level, then you zoom out and you simulate it at a bigger level, you know, like a bucket of water. That's actually what my master's thesis was on. It was a bucket of water and square meter, basically, of water, simulating using the Navier-Stokes equations for fluid dynamics. And then you can zoom out from that and simulate bigger bodies of water, like maybe in a pool, and then zoom out from that and simulate oceans where you have these big currents and things like that flowing around the world. And we're computationally limited, right? And so the resolution, if you're simulating the entire ocean, the resolution of scale is going to be like, you're going to have like 1 point every, you know, kilometer maybe, right? Whereas when you're simulating a bucket of water, you might have, or a square meter, your grid that you're simulating on might be every centimeter or more fine grained than that. And if you're simulating water molecules, you're going to be down at the, you know, nanometer level, simulating very, very fine grained stuff. So yeah, you have chemistry. Below chemistry is physics. Above chemistry is biology. And you kind of have to know where you're going and where you came from. Digital logic is the same thing for us. So computer science people do software, and software is sort of in between people, right? It's like user experience people is kind of the layer above us a lot of times, unless you do user experience stuff. But a lot of times computer science people don't worry about things like graphical interfaces and things like that. Like in this class, we're using a command line interface, which is utterly unsuitable for the common individual, right? But we do our stuff, and then somebody like Mr. Bell maybe builds a nice website that, you know, there's something called model view controller, and there's hundreds of variations on that. But basically, somebody's going to provide a view into your data or whatever that you're generating, and so that's like the interface to the users, right? And then we kind of operate down here where we're like going to be figuring out, you know, we're simulating water or whatever, and then somebody needs to build a view into it so you can visualize it and rotate it and play it through time and stuff like that. And then the level below us is the CPU. And so the software we write runs on a CPU, and that's that interface there, because we write C++ code. And so C++ translates our code down a level into assembly. And assembly is also not the lowest level. That gets translated down another level into object code. And so we go on the server. If we take that code that we just... So if we have our code here, This gets compiled invisibly. We usually don't see it, but it gets compiled invisibly into from C++ into assembly. Here's the assembly code. Then the assembler takes that assembly code and converts it into object code. You might have seen a .o file before. You probably haven't seen a .s file before, unless I've mentioned it, because it erases it. It compiles it to assembly, then it erases it. And if you're just going directly from a .cc into an a.out, it makes a .o file also, and then erases it. But it's there. So if we do a g++ -c main.cc, then main.o, this is the object file. Okay, so this is a level below assembly. And this is what, well, it's still not exactly what gets read by the CPU. This gets read by the operating system. And the operating system's loader, which reads this thing, kind of sets it up for the CPU to understand. And so there's layers on top of layers on top of layers on top of layers. Different layers of abstraction. Okay. And that's one of the problems with web developers, is that they live so far away from the silicon that they don't really know if what they're doing is fast or slow. It's so nebulous. A lot of times they write code that's very inefficient. And like there's this whole architecture of JavaScript packages, including other packages, including other packages, including other packages, and yeah. Anyway, so here's your object code, and then ultimately this gets processed by the CPU. Now the CPU is not the highest level; it's not the lowest level either. It's actually quite high level. Now we're moving into the world of computer engineering. So we were up in the world of computer science. Computer science covers this area, the .cc to the .s, and then once you start talking about .os and CPUs, now you're moving into the world of computer engineering. Computer engineering is the world of CPUs and digital logic, which is what we're talking about today, and how to build a CPU, how to make a BIOS, that kind of stuff. And so computer engineering is like the level kind of below computer science. We still have to learn some computer engineering. And computer engineers have to learn computer science, and they have to learn the layer below them, which is electrical engineering. Electrical engineering is below computer engineering. And then below electrical engineering is physics again. So that's why computer science people have to take some computer engineering. They have to take some electrical engineering. We have to take 2/4 of it. And you have to take some physics. So you have at least a decent understanding of the foundation upon which you are building. That's why all of that is required. So, and we talk about this stuff in 45. So this lecture today is going to kind of prep you a little bit for CSI 45, I guess. If you've already taken it, it's still interesting. Okay. So we're going to talk about digital logic today. All right, so logic gates, transistors, you might have heard the CPU has 5 billion transistors in it. We'll talk about what that is, and we'll probably get to the rest of this on Thursday, probably. Okay.
What we're going to do right here is go back. Way back into time.
So,
the only people that existed were troglodytes.
Troglodytes. Cavemen. Okay. I don't know if that came through on the speakers, but that was sampled by quite a few R&B rap people. Okay. Were you guys able to hear that? Who was it? I don't remember off the top of my head. You guys couldn't hear that? Go? Yeah? Okay. All right. So, there are these things called logic gates. And logic gates are basically the hardware equivalent of an if statement, kind of, or not like an if statement, but like the logical operators that we do in an if statement, right? Like in C++, when we say this and this. In electrical engineering, there is the physical hardware equivalent of doing and from C++, or not. And there are three basic logic operations, and or not. That's what we use in C++. In electrical engineering, and that's all you need. You can build any circuit, any if statement can be written with these three. Or there's also NAND, NOR, and XOR that are also pretty commonly used. If you have an SSD, you might have heard it's got NAND. Have you guys seen this? Like, it's a NAND MLC, SSD or something like that. Logic gates are what goes on under the hood. Yeah, logic gates is the fundamental building block of the CPU. Okay, and well, a transistor is, I guess, the most fundamental, but these things are built out of transistors. Okay, and we haven't quite gone down to that level yet, but we'll talk about transistors as well. But essentially, what you have in a circuit is you have voltage. You have a voltage. You have electrons flowing around. And so an AND gate works like this. Let's say that 0 is false. That's how it works in C++. In the physical hardware, let's say 0 voltage is false. 0 voltage means off. Nothing's flowing. Okay? And let's say that 5 volts is on. In a modern CPU, it's not going to be 5 volts, but it just makes for a nice even number. So let's say that 5 volts is on or true, and 0 volts is false or off. So what happens is, if you have a logic gate, you got a wire. The wire is carrying electricity, and then you have another one that, let's say this one is carrying 5 volts, this one's carrying 0 volts. And then you've got a logic gate. This is called an AND logic gate. Is the output, what do you guys think? If we've got true ANDed with false, do we get true or false? False, yeah. So it's going to produce 0 volts as output. Now, if this changed and suddenly we send 5 volts down the wire here, the result of this is also going to be 5 volts. Electricity comes flowing out. Okay? And so these are the fundamental building blocks. And it looks like this. Okay? You got AND, you got OR, you got NOT, NAND, NOR, and XOR. And these are the shapes that are used in electrical engineering and computer engineering. Okay, these are probably you should memorize them. You're gonna see these over and over again in your career. So the AND one looks kind of like a bullet. The OR one looks like a Star Trek communicator. NOT is actually so they draw it here as a triangle with a dot at the end of it, and that's technically true, but actually NOT is the dot. NOT is the dot. The triangle thing is actually a diode. It just means current flows this way. So that's why you see, like, you have NAND here, which is the AND character with a dot on it. The dot means not. And you have NOR, which is the Starfleet communicator here, with a dot at the end of it. And XOR, it's not a not. It is exclusive OR, which means one or the other, but not both. And that's drawn with an extra Starfleet communicator insignia line there. Okay. And so what you'll see in circuit diagrams is you'll see tons of wires, and they're hooked up with these primary symbols here. And you can sit there and stare at it and figure out what it is it's doing. And using technically just these three, you can actually, using technically just NAND, if you want to, you can build addition, subtraction, multiplication, division, memory, if you want to hold a bit, you can do so. And yeah, so all of the things that we know and love inside of a CPU, if statements, obviously. All of these things can be done just using these very, very simple tools here. And what happens is, if you're a computer engineer and they ask you to build a adder, let's say, what they'll do is you start small. Just like in computer science, you start small and you go slow. And then once you get something working, you zoom out and you reuse your existing stuff. And then you zoom out again. You zoom out again. And nobody builds a CPU from scratch with billions of these things. Like, there's not like, you know, it's not like you walk into Intel and they have like projected on the side of a building, you know, this circuit diagram, and there's people staring at it like, oh, well, there's the multiplier in here, you know. It's just this giant web of wires. No, that does not exist. What happens is that somebody builds an adder, and then they put a little box around it, and they say, this is an adder. And so that whole circuit for doing addition turns into just a box that has a line coming in and a line coming out, or two lines coming in, you know, X, Y, and the output, right? And then once you have that, zoom out, you know, I have a multiplier now, and the multiplier just looks like a couple adders connected together in a loop or something. And then once you have a multiplier, you zoom out, and you might have a ALU which does addition and subtraction and multiplication, no division, and or and not, and all of the arithmetic and logic, ALU, arithmetic logic unit. And then once you have your ALU built, you zoom out again, and you just drop the ALU into your CPU. And it ends up looking something like this. Yeah, so you have these blocks, right, and they just connect together, right? And so if you double clicked on one of these things and zoomed in, you know, you could look at the parts that make up these things, and you zoom in, you know, like this, right? And so really, okay, well, we'll just see this. And so you see here, there's an ALU here, and you know, there's a data cache here and a cache here, and each one of these things has tons and tons of logic units in it, right? But they don't draw it; it's too complicated. And so what we do is we just put a box around it. We just put a box around it. USB 2.0 ports, box. And then if you want to see what's inside of there, you double click on it and zoom in, and you can click and zoom in and click and zoom in, and but you can see all these things are just little boxes, and that's how we manage the complexity. Okay, so internet went out for a second. Let's see if we'll get back. Okay, so let's take a look at this. Okay, so what is this logic circuit doing here? Well, let's run through it. Let's make a truth table. Okay, let's try to figure this out. So Gregorian, you here? Okay, so Gregorian, you're my volunteer. So we've got A as an input. This could either be true or false. True means 5 volts, false means 0 volts, right? So if we have, we're gonna make a truth table here. We got A, we got B, and then let's just figure out this value here. Okay, so what voltage is gonna come out here? So if we've got true, 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 false, false, true, false, false. If we've got true on this wire here, if we've got 5 volts coming in here, let's do this one first. True, true. All right, so if B is 5 volts, 5 volts coming in this way. 5 volts are going to travel down this way. 5 volts are traveling down this way. Okay. How many volts are going to be after a NOT? So if we got 5 volts on this wire, how many volts are going to be coming out of this NOT here? So we got 5 volts on the input to a NOT. How many volts are coming out of the NOT? True becomes false, false becomes true. How many volts are going to be coming out of it? Gregorian. 0. Very good. Yep, so 0 volts will come out here. Same thing down here, 0 volts. So now we've got no voltage whatsoever. What is the output of this going to be here? False ANDed with false is false. 0 volts also there. Okay. So we're going to call this logic gate here Greg. Okay. So the output of Greg is going to be false. Okay, now let's do it again, but we've got true, 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 false. So this time the input to this, to B is false. So what is the output of this not going to be if the input is false instead? So if we're feeding 0 volts into a NOT gate, how many volts come out of it? Greg. If we send 0 volts into a NOT gate, how many volts come out of it? Greg, you there? I don't know. 5 volts. 5 volts come out. Because we're saying this is a 5 volt system. True becomes false, false becomes true. Okay? In reality, a CPU is much lower than that. Okay, so now if we're feeding in 0 volts and 5 volts into the gate named Greg, how many volts are going to come out? This is an AND gate. So both of these must be true for the output to be true. Still 0. Very good. So, okay. So the output of this is still false. And then false and true is the symmetric equivalent to that. So that's 0 volts, that's 5 volts. So it's the same thing, just in reverse. 5 volts here, 0 volts here. True ANDed with false is false still. Now let's go over the last one. So Greg, if we've got 0 volts here and 0 volts here, how many volts do we have on these two wires coming in here? We got 0 volts feeding into the NOT gates. How many volts are going to be out here? 5. Good. So we got 5 volts coming in here, 5 volts coming in here. When you do a true ANDed with true, how many volts come out of it? True. Good. 5 volts. So we would just write that as true. Okay. So this is a what kind of gate would you say this is? How would you describe this? It's only true when both are false. What kind of gate is this really? How would you describe this gate? Greg? What does this truth table look like to you? And Tomas has been typing for like a really long time now. Kind of scared. Oh, it's just the cursor. Okay. Greg, how would you describe Greg, the logic gate? What kind of operation are we doing here? And this is and, but we've got these two knots coming into it. So what we're doing here is a NAND gate essentially. So we could have rewritten this whole thing here as just this, an and with a little dot at the end of it. So A and B could have fed into it like that, and then the output of that would feed into here. Okay. So it's a NAND gate. All right, so let's move on to this one down here. This is just an AND gate. So We've got Greg as the top gate here. We've got Tomas as the bottom gate down here. Let's work out the truth table for this. So we've got A, B, true, 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 false, false, true, false, false. So the output of Greg is going to be true only when both inputs are false. False, 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 true. Then we've got Tomas over here. Tomas is just a AND gate. So Tomas is true anytime A and B are both true. So we got true, false, false, false. And now, what kind of gate is this, everyone? What kind of gate is our Star Trek symbol here? Starfleet communicator. It's an OR gate. Yeah. Good. All right, so this one we will call Connor. Okay, so the output of Connor is going to be true when either Greg or Tomas is true. Okay, so what we do is we look at the two columns to our left here. So Connor is just Greg ORed with Tomas. So false ORed with true, true, false ORed with false, false, false ORed with false, false, true ORed with false is true. So if A is true, if A has got 5 volts on it and B's got 5 volts on it, then the output of Connor is also going to be 5 volts. Okay? If A is 5 volts and B is 0 volts, the output of this is going to be 0 volts, vice versa. And then if they're both 0, Connor is going to produce 5 volts. So, how would you guys describe this circuit overall? The output of the circuit overall, in other words, the output of Connor, it's true when A and B are both true, or it's true when A and B are both false. How would you describe this? The total circuit. What is it doing? What is it checking for? What is the relationship between A and B that it is returning true for? Let's put it that way. This circuit returns true when A and B are both the same. Very good. This is a if A double equals B circuit. So this circuit returns true when A and B equal each other. And that is what an if statement looks like in hardware. So if you were to design this in hardware, you have a palette. On the left-hand side, you just drag out each of those logic circuits, hook them up, and then when you're done, you select this whole thing, and you say, put it into a box. And then it goes into a box, and you're like, what do you want to name the box? I don't know, let's call it double equals. And so it then creates a new box for you called double equals, and it's going to take in an A, it's going to take in a B, and it's going to return an output. And the output is true when A is the same as B. And that's how hardware design works. You start off at the very lowest level, if you want to. A lot of times, the chunks you want are done for you. And so, and then you can make a not equals, right? You can make a not equals by just taking this block here and putting a little circle, right, at the end of it. And then you can save that as a not equals block, right? So, it sounds like hardware just consists of true and false. In digital logic, yes. In digital logic, yes. There's also analog. Analog allows values between 0 and 1, right? And that's a completely different bag of fish. Okay? Digital design, yeah, everything is true or it's false, right? That's it. And so when you do hardware design like this, you're literally just writing if statements in hardware. And if you're like, man, it would be cool if somebody actually made like a programming language that would actually spit out the hardware for it, and that exists. So, so when you see electrical engineers making their circuits, and I'm not talking about in like a freshman level class. In a freshman level class, you're gonna have wires and smoke coming out and stuff like that, or at least if you're me. But if you look at the advanced people, then it looks like they're programming. It looks like they're programming. there's a variety of different ways of doing this, and what it looks like is it is a hardware description language used to model electric systems. So it's used in the design and verification of digital circuits. And so it looks like this. If reset, begin, do that. End, else, begin. Doesn't that look like programming? Yeah? What do you think? Input, clock, input, reset. Right? So this is actually not software. This does not run on a CPU. I mean, you can simulate it, but this is actually making a circuit. That it doesn't have to. You can use to verify a circuit, but basically this turns into the ands and ors and wires and things like that. So you don't have to click and hook everything up yourself. You just do it at a higher level. Okay. Looks like Python and C++, yeah, but it's not. It's not software. It's actually designing hardware. And so, what is this? Counter circuit parameter. Always, if, else, if, begin, else, delays, definition of constants. So yeah, and so when my double E friends are working on this kind of stuff, I'm like, oh, you're programming? Nope. I don't know how to program, man. Right? I'm like, that looks a lot like a programming thing. Nope, it's hardware. I mean, it's programming, but it's not. It's programming, right? So, yeah, and so you can design a circuit by dragging and dropping blocks around, or you can. There's these things called FPGAs, which are field programmable gate arrays, which are hardware that you can actually drop a program on, and it actually reconfigures the wires within itself. It's kind of cool, also. This is not how you do it with Arduino. Arduinos are not the same thing. Arduinos, you'd actually wire this up. So, I don't have an Arduino here, but I got a Raspberry Pi here. And so with a Raspberry Pi, there are these pins right here, and you can send 5 volts out on them. And then you can wire that into a circuit that has an AND gate. Like I have physical AND gates around here somewhere. It's in my garage, I think, actually. And you can wire, and so you have an AND gate that takes 2 pins as input and 1 pin as output. Wire it in, wire it in. If they're both true, 5 volts, then the output is 5 volts. If either of them is 0, it gets 0 volts. And you could physically wire this up if you wanted to. And we do that in CSI 45. Sit there and wire things and turn LEDs on and stuff like that. So, but the hardware description language, hardware design language, that actually is used to generate hardware or to reprogram an FPGA. Which an FPGA is this. You can think of it as a bunch of logical wires and AND gates and OR gates that can actually move. So the wires, they don't move, but you think of it as you can go click, and you can attach things to each other, and you program it, and the thing actually reconfigures itself, and so you can make your own CPU. It's not usually you don't use it to make a CPU, but for your own specific, if you want to do Bitcoin mining, then you reconfigure the hardware on the FPGA to do Ethereum hashing or whatever it is you're trying to do. Okay. So, yeah. So when you take a digital logic class, which you probably will, depends on which college you go to. I can't guarantee it. But if you go to Fresno State, you're gonna take it. If you go to UCSD, like I said, you have to take 2 quarters of electrical engineering, and 2 quarters of digital logic as well. So you're gonna do a little bit of hardware. Most of your stuff is software, but you do dip down into it because, like I said, it's important to know what's going on. So you start off by wiring together ands, ors, and nots, and then you save them as a logic block, and then your palette has and or not, and it's got double equals, and you can now drag that in. Yeah. And then you build a bigger thing, and Now you save that as a block and you can drag that in. And so people operate at high and low levels of abstraction, right? And we sort of navigate up and down within the levels of abstraction to keep it simple for our human brains. Okay, so I'm not going to torture Greg anymore with this one. I'll just tell you this is a bit of memory. So we got here two NANDs that are wired into each other. And so what happens here is this is how you save one bit. So it is a SR, it's what's called an SR latch. Multivibrators. It's a bistable multivibrator. That's one. Yeah. So basically, if you pass in, this is not S and not R. So if you pass in 1 for set and 0 for reset, these are knotted. So if you pass in 1 for set and 0 for reset, then the output is going to be 1, and it will stay 1 until you do the opposite. And if you pass in 0 to these, then it retains the state. So basically, you can say set this bit to hold 1, or set this bit to hold 0, and you can't pass in true for both of them. That doesn't make any sense. So if you pass in true for set and 0 for reset, then that thing is going to be outputting high voltage 1 the whole time. If you pass in 0 for set and 1 for reset, then it resets back down to 0 volts, and it's going to be outputting 0 volts. If you pass in true for both, it breaks it. It's not allowed. And if you pass in 0 for both, then it retains whatever state it had before. So this is a very, very simple way of holding a bit of RAM. Just like that. What do you guys think? I think it's cool. Yeah, the design of RAM for like DRAM is completely different from this. But like if you just need a circuit that holds on to a bit, there's a whole bunch of ways of doing flip flops, but this holds a bit. And if you just need to have a circuit that holds on to a bit of RAM, and then you can feed that into an if statement, and then later on you can be like, all right, turn that thing off and set the reset. The output of Q becomes false, and then you can turn off blocks of your hardware. So it's like a variable. This is a variable, a 1-bit variable. If you want 2 bits, make 2 of them. You want 8 bits, make 8 of them. Drag a box around them, make it a logic block. Great, you got 8 bits of RAM now. You got an 8-bit register. You want 32 bits? Copy paste 32 times. Drag a rectangle around it, make a block out of it. You now got a 32-bit integer or whatever. Feed that block into an adder circuit. Drag it out again, feed it into an adder circuit, and then your adder circuit you have to make does 32-bit addition, and it produces another 32-bit variable. Like, that's what you're going to spend a couple semesters doing, that kind of stuff. But that's kind of it at a high level. Okay? So, yeah, just really simple stuff, right? This is equality. This is a bit of RAM, and there's different ways of doing flip flops, like I said. Yeah, and then so you select all this, you like save it, and then there you go. So that's that's what it looks like. So you start with this, you turn it into a block. The inputs and the outputs are retained. You guys see that? So S, R, Q, not Q. The inputs and outputs are retained, but all the guts in the middle just turn into a box. And that's hardware design, And then you zoom out, you zoom out, you zoom out. You just have your inputs, your outputs. If you have 8 wires, like if you have a 32-bit thing, like you'd be like, is there going to be like 32 different wires coming into it? That seems really excessive. And what they do is they draw one wire and they put a slash on it and they say 32. So to keep it simple for our human brains, right? So they'll just do that, and that's like behind the scenes. There's actually 32 different wires, but it gets really complicated to draw. If you want an 8-bit input, you just do it like that. So initially they're a box. No, initially they're this. So that's a NAND gate. At the very most basic level of hardware design, you've got AND, OR, and NOT. And if you feel like it, NAND, NOR, and XOR. That's just with those, technically just with NAND and wires, you can build an entire Core i9 CPU with just NAND and wires. That's it. Your palette has 2 things on it. NAND and then a wire tool that connects them up. That's it. Build the entire colossal edifice of human civilization, which is all built on transistor-based CPUs, right? All of it can be built using NAND and wires. It would take you a while. It would take you a long, long time, but you can do it. So in order to make it possible for us to accomplish things in a reasonable amount of time, what we do is we select all of this and say make a block out of it, and then that gets added to our palette, and we drag it out. Let's go and show you what that looks like. Logic works. Yeah, so like I said, you just drag out these boxes and you wire them up. This goes into a data bus, and then it's splitting the wires back out. And then they're hard coding true and false onto these things. You can look at the output of things as you set things to be true. True is high voltage, false is low voltage. I don't know what that has to do with anything. Yeah, but that's essentially what you do. And yeah, you just turn anything into a box, and you can click on these things and they'll switch between true and false. And then you can have outputs that are LEDs, and they'll turn on and turn off, and so you just can do that to test your code, right? So you just boom, 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 and oh look, it turned on. Cool, you know, neat. The IFs are on. It's funny. Yeah, and so a lot of these techniques you learn about testing and things like that, they apply in the digital space as well. Okay, so the box is just simplifying it. Yeah, so if you were to double click on that, it would actually pull that up. So if you wanted to see what's inside of that, you just double click and it's like, oh, cool. And then you go back. Yeah, and then, yeah, you simplify over and over again. So this one here is another flip-flop. This one, I think is a delay flip-flop, a D flip-flop, which retains a bit for one cycle. Inside of a CPU, you've got a clock, and if you've ever heard of the clock speed of a CPU, like I have a 4 gigahertz processor, that means there's a clock that goes high and goes low, 5 volts, 0 volts, 5 volts, 0 volts. It's actually not 5 volts, but again, I'm just using it because it's a nice round number. High, low, high, low, high, low, 4 billion times per second. Okay, and so D flip-flop holds on to the D flip-flops. Yeah, and that's what the block looks like here. Should have a clock coming in. Yeah, a pulse steering circuit here. Clock, there we go. Yeah, so the clock, when the clock goes high, it sets the output value to be whatever the input is, and then when the clock goes low, it retains it. So it basically is a delay flip-flop. It holds on to a bit for one cycle. Clock goes high, it sets the output to be whatever D is. Clock goes low, it retains it. And so you can use this to synchronize and stabilize a circuit, so that, you know, when the clock's low, everything kind of evens out, and then you can do clock high, and then you can do your addition. Clock goes low, everything stops, because nothing stops at exactly the same time, right? It takes longer for electricity to flow this way than it does to flow this way, because you got a third gate in there maybe. So you put in a delay flip-flop to allow all the voltages to kind of even out, and then the clock goes high again. Now You do one more arithmetic. Clock goes low. Let all the voltages even out. Clock goes high. All right, do one more arithmetic. And so, generally speaking, if your CPU runs at 4 billion gigahertz, 4 billion hertz, then you can do. It's oversimplifying, but you can do like 4 billion additions. If your clock goes high and clock goes low 4 billion times a second, your CPU can do 4 billion adds a second. Clock cycles. Yeah, 1.262 volts. Yeah, that sounds about right. No modern CPU that I'm aware of runs at 5. That's like super overclocked. The reason why I pick 5 is because that is the output voltage on a Raspberry Pi. And so I want you guys to get used to it, because that's when you're actually doing the wiring, it's going to be a 5 volt output. Okay, so this is what it looks like. So if the data is high and the clock goes high, the output's high. And then if the data is low and the clock goes high, it goes low. And so it retains the output until the clock goes high and the data is low. Does it differ depending on OS? No, this has nothing to do with operating systems. We're down about 5 levels below the operating system right now. So the your inside of your motherboard somewhere, you've got a clock generator, and that clock is producing a, let's say, 4 gigahertz signal. High, low, high, low, high, low, square wave. And no square wave is perfect, by the way, because it's got a it has to transition from high to low. So you can see there's a little bit of a slope on these things here. See if we can zoom in on that. This is like what your clock is producing. Your clock goes high, goes low, goes high, goes low, and there's a little bit of a slope on that. That's called the slew rate. The slew rate is how quickly it can transition from high to low. And so all the circuits that work on, is the voltage above a certain threshold, once that thing crosses the line, they start operating. And once the thing drops below the line, like I said, if you have a D flip-flop in there, then when it's down here, it just retains the value it had before. Then when it goes high again, it does one more addition. And then when it goes low, it stabilizes. Go high, one more addition. Okay. And so it does this 4 billion times per second. And what is it doing? Well, on my system, it's currently streaming my face over the internet. It's on Discord talking to you guys. And all that is just this. Right? If you want to think of it as all just wires and Nand gates. Hi, you can see me. I'm streaming. What the hell? What the hell? Like, do you understand like how mind-blowing that is? Like, at the lowest level, this is all you're talking about. There's a clock, it goes high, it goes low, and all the circuits like run one cycle, and somehow I'm able to speak, and like, that's how many levels of abstraction we are away from this. Right? Is that I'm able to just click and join Discord, and people are like, oh, Discord's not working right. Like, do you understand what a miracle it is that anything works at all? That my CPU doesn't crash a billion times a second, like it's it's ridiculous, like, that it works. Like, none of this, like, if you had to design this whole thing from scratch, like, society got sent back to the Stone Age, there's no way of just like, you're in a cave somewhere. You're like, all right, I know digital logic. I'm gonna make a CPU and make cell phones again. You know what I'm saying? Like, there is just like, you just can't do it. Everything is standing on top of something else, Like, you would have to start off by like inventing blacksmithing and spinning out wires, and like, you'd have to reinvent all of human civilization if, like, it's ridiculous. Hieroglyphs or Intel schematics, yeah, it's fun. Okay, so this is the last thing, and then I think I've hurt your brain enough for today. So we'll just call it here. But sometimes on a truth table, you will see an X. Okay? So you might be like, wait. I thought things are either true or false. They're either 0 volts or whatever high volts is. I've been saying 5 volts. In reality, it's not. What? Huh? How can you have something else? And the answer is this is the same circuit as before. The SR latch, but with a clock. And so when the clock goes high, the circuit works. When the clock goes low, the circuit turns off, and it stabilizes. So when the clock is off, it does not matter what R and S are. That's what the X means. You notice how this truth table should have 8 entries on it, right? For every combination of true and false, true and false, true and false. 2 to the third power is 2, 4, 8, right? But we don't. And the reason for that is because when the clock is low, nothing happens. When the clock is low, you AND these two things. 0 ANDed with anything is 0. This is 0. That is 0. Nothing changes in an SR latch when the inputs are 0. Remember, when both are 0, it just retains the output. So when the clock is low, it literally doesn't matter. R could be high, S could be high, it doesn't matter. If the clock is low, the output of these AND gates are going to be false, right? False ANDed with anything is false. False ANDed with anything is false. It does not matter what S and R is. So we just put down an X there. The X means we don't care what the value is. It does not matter. This is the melodramatic teenager equivalent in electrical engineering. Don't care. What is it? I don't care. What do you want to do for dinner time? I don't care. So, so when the clock is low, it does not matter what S and R are. And then, and that's one kind of don't care. The other kind of don't care is if you've done goofed, if somehow you passed in true for both of these things, you can't have true. You can either have S be true and R false, which will set the value to be true. You can have S be false and R be true, which sets the value to be false. You can have both false, which leaves it as is, but if both are true, it's undefined behavior. And so in this case, the X means undefined behavior. Who knows? Who knows what you'll get? It's like a division by 0 or an infinite loop or something like that. Who knows what the out's going to... Like, when that clock goes low again, it's going to be some value. It'll be true or false, but don't know which one it is. Could be either. Just depends on how the individual electrons are feeling that day. It's random, almost, maybe. Okay? So, X's can mean two things. One, it means it doesn't matter. And the other one means it's undefined. Right? In this case, it's defined behavior. If S is true and R is true, or S is false and R is true, it does like for all 4 combinations of true and false for these things, the output's going to be no change because the clock here. This is defined behavior. This is we know exactly what it's going to happen. When clock is 0, it retains the bit that it's holding. For this one though, we don't know what the output's going to be. And so we just mark it as X, which means we don't care. If the person that's calling our circuit screws up, that's on them. It's not our fault. We're not going to handle it. Okay? So, X means don't care. And then, So, you know how I was saying, like, you could do everything with NAND? Everything could be done with NAND. This is a NOT gate. This is a AND gate, because it's a NAND with a NOT. So that's AND. You can make AND out of NAND. Right? If you feed A into both inputs on NAND, true becomes false, false becomes true. So that's a NOT gate. You make a NOT gate using a NAND gate. And if you attach a NOT gate to a NAND, you get AND. Hey. And if you have NOT feeding into NAND here, then you get a OR gate. Let's see, not. So not A NANDed with not B. Should be OR, yeah. So that's a OR gate. And that's a NOR gate, because it's an OR gate with a NOT on the end of it. That's I don't know, my brain's kind of reaching the end. of what I can encompass quickly. But let's see, XOR and then not XOR. Yeah, cool, called it. All right. Yeah, so that's an XOR gate and that's a not XOR gate. So you can use NAND to simulate every other type of logic gate. So you could build literally an entire Intel CPU out of nothing but NAND gates and wires, if you wanted to, which you wouldn't, but you could. Aaron, do you understand this one at least? If you pass in true and true, you get false. If you pass in false and false, you get true. So this is a NOT gate, right? And then a NAND with a NOT is AND. This one, if you go through the truth table, is OR. This one is going to be NOR. And then this one, yeah, you'd have to sit down and like sketch out the truth table on it, but it's XOR and this is a not XOR. Those two, yeah, exactly. It gets complicated enough that you need to actually like work it out. Yeah, and then we'll talk about transistors next time. Okay, so that's it, everyone. We'll just call it here. Work on your homework assignments, and I'll see you on Thursday. What's going to be on the exam? Everything. No, hash tables, I think. I think we'll do one hash tables. That seems important. Okay. All right. See you guys.